So this webcast is totally dedicated to Bisokotuwa, which is a very important element of Sri Lankan reservoirs. So Bisokotuwa is built to control the water flow, volume, and also the water pressure. There are two types of pressure control system. One is the Bisokotuwa, and the other one is called the Kata Sorowwa, which we are going to discuss both of them. And why do we need this structure? So let's go to this figure here. This is a reservoir. This is the bund. And when you have a reservoir, the type like big reservoirs around 70 feet of water column, this water column stretches for miles. This 70 feet stretches for miles. And when you try to take water out of this sluice here, what's going to happen is there's going to be a lot of turbulence here. A lot of turbulence. The water is trying to gush out from here. And in the process, due to this turbulence, this bund is going to get blasted away. And these reservoirs are very dangerous in the sense that if they get blasted away, the villages downstream are going to go under and people are going to die. So I'm going to show you videos that I found in YouTube. In this one, you could see this is not a bund failure. This is not a bund failure. This is basically water coming out from the spill, from the top of the tank. And you could see this bridge is gone under. See the power of this water I'm trying to see. Okay, you could see here the water is spilling out from the top. And just imagine, I'm trying to locate the bund. Okay, so just imagine this bund was gone. This is just normal spilling out. See, this is the bund, actually is the spill. The water coming from the top of the spillway, and just imagine this is gone. Then all that water in Kala, miles long water, is just going to gush down, and you're going to see a lot of destruction. So how would this happen now? How would this happen? So now we are going to try to take water from these big reservoirs. So the water is going to create a lot of turbulence here. The water is going to flow, and this bund is going to fail from there. So you need a way to control this water flow, and that's why they built this Bisokotuwa. They built something like this, which we are going to talk in detail. So the water comes here and goes up there. There's an energy loss here due to turbulence happening here, and when the water goes from here, there's friction, and that friction would take out some of the energy, and there's friction here. Also, these conduits or little tunnels could stretch for like 100 meters in some locations. So the Bisokotuwa could be far away, or Bisokotuwa could be close by in some of them, or this conduit could be far away. So they design in different ways the Bisokotuwa. So basically what we are seeing is that without Bisokotuwa, it's going to be extremely difficult. Without some kind of a pressure control system and a volume control system, it's going to be very difficult to build large reservoirs. So if there's a reservoir somewhere in the world with a water column of, let's say, 70 feet, then you have to ask yourself, how did they take water out of this? How could they take water out of this? They have to have a method or mechanism. So that's why I believe that the Bisokotuwa is instrumental to building these large reservoirs. And if not for this design, then what you are going to see is small reservoirs with village type tanks around the country. If that is the case, that the huge civilization that Sri Lanka had, millions of people in Anuradhapura, would not be possible. It would not be possible for that civilization to have people to build all those dagabas and militaries and etc. So this is very, very instrumental to building large reservoirs. And so in that sense, this is a very important part of Sri Lankan history. Whoever designed this created a civilization, created this big civilization. Otherwise, you're going to see little village tanks here and there, and large reservoirs of this nature would be impractical. And so that's the importance of Bisokotuwa. So this one I obtained from, I should give credit, R.W. Ratnakar, Director of Water Resources and Planning, Ministry of Irrigation and Water Resources. So these are some of the photographs of Bisokotuwa, and this is, this is taller, normally taller than this, and so there's a conduit underneath here, and the water would come through the conduit and go from there. And this is the Urusitawa Bisokotuwa, and this is another one. And here you could see some holes cut in the rock that we believe they could have had some kind of wooden doors in these Bisokotuwas to so the wooden door could be lifted up and down to control the flow volume. And this is another photograph of Bisokotuwa. It's a small one. This is another photograph. This could be a sluice gate, but could be a Bisokotuwa too. And this is the tunnel that they have. Once the water comes to the Bisokotuwa, it goes through this tunnel, and this hole at the end is smaller than the tunnel itself, and in some designs, and so you would not get water going through these joints in the rock into the bund. So the water is, there's another design you could do. You could take water from far away, and they have done that too. But in this case, you cannot control you keep the bund safe, because now the turbulence is not here, the turbulence is here. So you keep the bund safe, but now you cannot control the flow. You cannot put a gate here. So you need to have a gate to control the flow. And that's why you have something like this. So here you have the Bisokotuwa, water comes here through these holes, and there's energy loss here, and the water goes through. So in this system, this is the earlier system, that the energy is dissipated due to friction in this pipe, and these conduits could be 100 meters or more. And also energy dissipated in the Bisokotuwa. When the water comes here, there's going to be turbulence. That turbulence would dissipate energy. And now in this design, where they have gates, you could control the flow. You could lift this up halfway and then let the water come in to whatever the amount you want, and then you lift it up here, and then the water would go nicely. Your pressure head is here. You're not going to get large flow volume, uncontrolled flow volume at the end. So this is another design, and you could see this is the plan view. They have this type of one conduit coming, and it's Bisokotuwa, and then there's another one, and then some Bisokotuwas, they made it an angle. So there's energy loss in here too. So energy loss at the bend, and the water would go like this. In Urusitawa, you have one conduit bringing water and two conduits taking water. So if you want little bit of water, then you close this conduit with the gates, wooden gates, and let the water go from this one. And if you want a lot of water, then you open both gates. And also you could control the amount of water coming into the Bisokotuwa with the gate here. So, and in other reservoirs, some reservoirs, you have conduits coming like this and going like that. So the water comes here and hit the wall here, and there's another way to dissipate energy. So that's another design. Now we look back at Kata Sorowwa. There's another form of equipment to reduce the pressure. In this case, you're taking water from the top. So let's look here. So this is the Kata Sorowwa, and this is a Kata Sorowwa with a protection structure. So the water comes here like a Bisokotuwa, and then water flows up and goes like that and goes out. So Kata Sorowwa is inside a protective structure. Water comes in, goes like that, and then goes out. The problem with this is that the water is not under heavy pressure. So you're going to get very little flow. Now you could have the Kata Sorowwa without any protection, and in that case you may have to do repairs, etc. Again, this one, water just slowly goes over here and goes like that. Now if the water level goes down and we need to take water out, then you remove these Kata, and then remove up to here, and then water would go like that. And if you don't need water at a certain point, then you increase this Kata. So that's why it's called Kata Sorowwa. So you increase these little structures on top of that. So you could control the flow. You could shut it down, and if you want more water, you would, let's say the water level is here, and then you would have your top here. You remove everything. So you would have top lower, so the water would go like that. And if you want more water, you could bring it down. So, but this is for smaller reservoirs. This is not good for big reservoirs like Kalawa. It's not going to work. This little structure is not going to work. You saw the water column coming out from Kalawa. This is just going to get blown away. This is good for smaller. Probably looks like 10 feet, 15 feet. Even 15 feet is too much. Probably like 10 feet reservoirs. So that's the mechanism of Kata Sorowwa, and we will be talking about engineering aspects. But before that, I want to talk about something else. So we saw that there are two methods. One is the Bisokotuwa, that is taking water from the bottom, and then the Kata Sorowwa taking water from the top surface of the reservoir. And initially, we had little ponds when King Vijaya came to Sri Lanka, and there was a pond, and Kuweni put Vijaya's people in this pond. So there were ponds, and also it says that Kuweni gave rice to Vijayan people. So there was rice cultivation when King Vijaya came, and they used ponds. And they probably gathered water, rainwater, and then later, they built sluice, spill, and canals. And these small tanks can capture water from rainwater, and but Minneri, Kaudulla, Padaviya, those big reservoirs are too big for rainfall alone. So what they have to do is they have to build anikats or amunu. In anikat section I talked about, I have photographs and everything on large anikats. They made with cut granite. They put piled up over each other like nice structures, and they built long canals with very delicate slopes, and then they brought water from these permanent rivers, Malwatuoya and Ambanganga, a branch of Maveliganga, and fill these reservoirs. So now we have huge reservoirs, and there has to be a way to get water out of these reservoirs in a controlled manner, and that's where the Bisokotuwa came in. And as you saw on that video, without this Bisokotuwa, you are going to be having these failures of bunds in a very, very oftentimes, and these failures of these big reservoirs going to create a lot of damage, and it's not a feasible thing to have these big reservoirs without Bisokotuwa. So these are the photographs. I went through them, and so the turbulence is what going to damage the bund here, and you take it out, and now you have this structure here, Bisokotuwa, with doors. So you could control amount of water coming in, and there's energy dissipation here, and then you could control what is. So this basically can control your, this is called the head, or the pressure head, or it's due to gravity. So you could control this. If you want more water, you let it go up here, and then you get more water from there. And these are the plan views that I just showed. Some reservoirs have inlet 90 degrees to the outlets. So, and this is the Kata Sorowwa, that you take water from the top, so you don't have too much pressure going on. You could have a protective structure for the Kata Sorowwa, or you could have as it is. But this is good for small reservoirs. This is not for big reservoirs. So now we are going to talk about engineering aspects of Bisokotuwa, and if you're not interested in it, you could cut away. But I decided to include that for people who are interested in engineering. So without Bisokotuwa, we would have a situation, we have a sluice, we have a conduit coming like that, and the water, when going from A to B, there's energy at point A and energy at point B, and there's a loss, the loss of energy here from this conduit and this Bisokotuwa. And so your kinetic energy, the water flow coming out, is much less than without this structure. So we could have this equation here, energy at point A is equal to energy loss in this structure, in these conduits and in the Bisokotuwa, and plus energy at point B. So energy of water, now assuming these conduits are flowing full, if they are not flowing full, we don't have pressure, then we need to have open channel flow. But I'm considering, and in most cases, these conduits would be flowing full, because in large reservoirs there's a big pressure head. So energy at point A is due to three things. One is due to gravity, the height of the water column. One is due to velocity, and the other one is due to the pressure at this point. And the energy loss has to be calculated. So this is the equation, basic equation, the HA. This is the kinetic energy, this is the pressure energy due to pressure, and this is the energy at point B, and this is the energy loss in the tunnel, and this is the energy loss in Bisokotuwa. So energy loss in the tunnel, you have equations like this. This is the diameter, or in this case, if it's a rectangular, you could take the cross width, and the area of the tunnel, V is the velocity, L is the length. And the problem is finding the energy loss in the Bisokotuwa, and it's a function of inlet velocity, out velocity, area of the tunnel, inlet tunnels, area of the Bisokotuwa from the plan view, and area of the outlet tunnel. So this has to be modeled, and I have seen people modeling it in various papers. They make small structures like Bisokotuwa, and they find the flow rates and pressure and all that, and then they try to model this. And what they have found in one paper is that the pressure loss in the Bisokotuwa is very high. The energy loss, actually I should say, not the pressure. energy loss in the Bisokotuwa is very high due to turbulence. So that way you could control the flow, and for different configurations, you could have slightly different equations. So this is basically how we are going to calculate the flow or calculate the velocity of the flow. And of course, they didn't have these equations at that time, so they probably did by trial and error. What they did was, so they built the Bisokotuwa, they build something like this, and they see what's the flow rate here. If this is too much, before the gates come in, once you have the gates, I think this is a evolution of this one. Gates came in later. Once somebody got the idea of putting gates here, then everything is controlled. But before the gates, the water would just come in here, energy loss, and then water would come out. So you could see the evolution of the technology. So I want to say that Bisokotuwa is a very important structure for the Sri Lankan civilization. Without this, I don't know how they are going to have those big reservoirs. These big reservoirs are very dangerous structures, as you could see, and the water is not something to be taken for granted. If these bunds fails, all downstream would go under. And so you need to have a way to control this water flow coming out from these reservoirs. And that's exactly what Bisokotuwa did. And as you could see, just imagine controlling these huge reservoirs without failure for a long time. And so without Bisokotuwa, you would be limited to small village level tanks, and these type of reservoirs would be like an out of control elephant. You cannot control an elephant without chains. So the Bisokotuwa is like a chain on an elephant. If you consider this reservoir as an elephant, Bisokotuwa is like a chain. It's control the reservoir, the dangerous nature of the reservoir, and it allows peaceful agriculture, because otherwise, without that, if you're trying to take water out, you're going to breach the bund.